Let's continue our study of AC circuits by considering a series combination of a capacitor and a resistor and an inductor all together with the alternating voltage source. Since they're in series, keep in mind that at any given instant, the current through each circuit element is the same, but the voltage differences don't have to be the same. On the other hand, all of the voltage differences will have to add up to zero if you follow a complete path in accordance with Kirchhoff's loop rule. In order to get a feel for how this works, we're going to introduce a vector-like quantity that is called a phasor. Phasor has a magnitude and a direction like a vector, but a phasor is different because, unlike a vector, a phasor is intentionally designed to rotate around in a circle, as we'll see in a bit. We take advantage of this phasor idea because of the fact that the current is going to be the same through all of the circuit elements. But the moments of their oscillations in their voltages will not be in sync with each other necessarily, nor in sync with the current necessarily. So this out of syncness is going to be represented by the phasors. Keep in mind that when we look at the current through the circuit, the voltage across the inductor leads the current, the voltage across the capacitor lags behind the current, and the voltage through the resistor is exactly in sync with the current. And we imagine plotting these in kind of an XY coordinate system. The voltage across the resistor being in sync with the current, we will plot directly along the horizontal axis. But the voltage across the inductor being ahead by pi over 2 radians, which is equivalent to 90 degrees, we'll have along the positive y-axis, and the voltage across the inductor being behind the current by 90 degrees, or pi over 2 radians, we'll have pointing along the negative y-axis. These three arrows represent phasors, and they are going to be treated as rotating about the origin of this coordinate system. The x-axis is where all the action is happening. The y-axis doesn't mean anything, but the x-axis, if you think about the projection of each arrow onto the x-axis, what you'll see are alternations, right to left and back again along the x-axis, and those will represent the actual oscillations of the device, of the voltage in the device in question. Phasors are a bit like vectors in that we can graphically add them together. Remember, we said that Kirchhoff's loop rule applies. Well, the voltage difference across the inductor plus the voltage difference across the resistor plus the voltage difference across the capacitor has to balance out with the voltage supplied by the source at any given instant. So what we can do is we can graphically add together the three phasors for those circuit elements, just as you would graphically add together things with a vector. And then the net vector starts with the beginning of the first vector and ends with the tip of the last vector. And in accordance, as I said, with Kirchhoff's loop rule, this better add up to the vector of the voltage supplied by the voltage source. The angle that the voltage source's voltage makes with respect to the horizontal axis means that it is out of sync with the current through the circuit. And this voltage across the voltage source is out of sync by some quantity phi measured in radians. And we're going to work at understanding how to determine the value of this phase shift. Just as I said earlier, We really represent these phasors as orbiting an origin. This is going to be a really cheesy animation because PowerPoint is not for sophisticated animations. But if you can imagine the tips of those arrows, the bases of those arrows, I guess, fixed at the origin as those arrows rotate around. And those arrows always maintain the same relative orientation with respect to each other. It is the projection of the arrowhead onto the horizontal axis that gives us the actual oscillations that are taking place. Much like the projection of the ball going around the circle on the left can be projected into a single axis represented by the ball oscillating up and down along the straight line to the right. And it's a little bit of a misconception, or it wants to kind of propagate a misconception by having the current be the primary reference for all other measurements. This kind of removes a cause and effect. Really what's happening is we get the voltage of the source that is driving the system, and everything else is a consequence of that. The current is not the cause. The voltage supplied by the external source is the cause. But we measure things with respect to the current because that is simply the most convenient. Remember that the voltages across the circuit elements were either parallel to the current or they were at 90 degrees with respect to the current. And that makes things a lot less painful. But in reality, it's the voltage of the source, like the black arrow, that's driving the system that is the cause, and the current is the effect. Take a look at this question. We have an RLC circuit hooked up to an AC voltage source. And the question is, which of the following is true? Does the potential energy oscillate between the capacitor and the inductor? Does the source do no net work, energy lost in the resistor being compensated by energy stored in the inductor and capacitor? Does the current through the capacitor, is the current through the capacitor 90 degrees out of phase with the current through the inductor, or is the current through the capacitor 180 degrees out of phase with the current through the inductor? Think about it. If you have questions, ask at the start of class. How do we find the phase shift phi? And for that matter, I want to find some more detailed information about the actual voltages across each of the different devices. And I want to find information about the current through the circuit. How much information can I get? Let's assume we know the value of the resistance, the value of the capacitance, the value of the inductance, and the frequency of oscillation of the voltage source. That last bit is important in determining XC, the capacitive reactance, and XL, the inductive reactance. You might want to review the previous lecture to understand those quantities a little bit better. The maximum voltage across the resistor is equal to the maximum current through the circuit times R. The maximum voltage across the capacitor is the maximum current times the capacitive reactance. The maximum voltage across the inductor is the maximum current times the inductive reactance. There are no promises that VR max, VC max, and VL max are equal to each other. In fact, you have to assume, just through random selection, that they will be different from each other. The nice thing about using the phasor diagram is that you can see that the voltage across the inductor is always going to be opposite in direction to the voltage across the capacitor. And so when I want to come up with a numerical value for, say, the phase shift phi, the contribution between the inductor and the capacitor is simply a matter of subtraction because they point in opposite directions. The difference between the voltage across the capacitor and the voltage across the inductor is going to be 90 degrees out of phase with the voltage across the resistor. So we can then use, so once we subtracted VL max and VC max from each other, we can use that result in kind of a Pythagorean fashion. VR is the one side of the right triangle. The difference between VL and VC is the other side of the right triangle. And the hypotenuse of the right triangle would be the voltage supplied by the source, just like the black arrow in the picture a few slides back. If we apply some Pythagorean business to this, we can say that the right triangle's hypotenuse is equal to one side squared plus the other side squared, take the square root. Well, one side is the voltage across the resistor. The other side is the difference in voltage between the inductor and the capacitor. So I take that difference, I square it, I add VR to it, or the square of VR to it, and then I can take the square root, I get the hypotenuse, or the magnitude of the voltage supplied by the source. If I wanted to, I could divide everything by current I, and I would get that this net voltage divided by I is equal to the square root of inductive reactance minus capacitive reactance squared plus resistance squared. That business on the left in the lower equation, V net over I, is just like in Ohm's law going to be a quantity that acts like resistance. But it's not exactly resistance. It's not exactly resistance because it depends on frequency. But we want to give it a word like resistance because it does act like resistance in many ways. So we're going to use the word impedance. Impedance is represented by a capital Z, and it has units of ohms. But as I said, because Z depends upon XL and XC, and both of those depend upon the frequency of oscillation, this isn't a true resistance. It just has some hallmarks, some characteristics of a resistance. With this definition of impedance, we can express a variation of Ohm's law using maximum values, so the maximum voltage equals the maximum current times the impedance, or equally valid, I can use root mean square values. VRMS equals IRMS times Z. Further use of right triangle mathematics would tell us that the tangent of the phase shift phi is equal to opposite over adjacent. The opposite side is the difference between the voltage across the inductor and the voltage across the capacitor. The adjacent side is the voltage across the resistor. So I can say that phi is equal to the inverse tangent of VL minus VC all over VR. But similarly, I can also say that the phase shift phi is the inverse tangent of the inductive reactance minus the capacitive reactance divided by R. There's one very important situation in RLC series circuits, and it arises from the fact that the voltage across the inductor and the voltage across the capacitor are always exactly opposite to each other. Because both depend upon frequency, it turns out that there is a frequency at which VL and VC will always exactly cancel out. And that's going to result in the smallest possible impedance in the circuit. In the situation where it exactly cancels out, the only non-zero contribution to the impedance is the resistor R. And in fact, in this very special circumstance, the impedance is equal to R. If you have a circuit with a very small resistance, just entirely wires without any resistors in it, that means that you are going to have an impedance that is dramatically small, and for an applied voltage, that's going to result in a current that is extremely large. The condition for this to happen is the same as saying that the inductive reactance equals the capacitive reactance. And if you go through the algebra, what you get is a requirement for the angular frequency for it to be equal to 1 over the square root of L times C. At this exact particular angular frequency, the system has the smallest possible impedance, and we say that the system is in resonance. You might want to click on the simulation. It takes you to a website where you can play around with V and R and C and the frequency and maybe get a good feel for how these different quantities interact with each other. Let's take a look at a somewhat painful example. So we have an AC voltage source and an RLC series circuit. We're told that the RMS voltage of the source is 120 volts and it's at a frequency of 60 hertz. So this is very standard quantities for the United States. We're given values for the resistance, inductance, and capacitance. 55.3 ohms, 258 millihenries, 79.3 microfarads. And we're given this question, after 0.108 seconds, what is the current in the circuit, assuming the initial current is 0, and what are the voltages across each of the circuit elements? And for that matter, what is the resonant frequency of this circuit? The circuit is not necessarily at the resonant frequency. There's no guarantee that 60 hertz is the resonant frequency of the circuit. Given that the frequency is 60 hertz, the angular frequency of the circuit is 2 pi times 60. It's actually 377 radians per second. That allows us to calculate the inductive reactance, which is omega times L, and the capacitive reactance, which is 1 over omega times C. So now we have R is 55.3, XL is 97.3, XC is 33.4. This allows us to calculate the impedance, XL minus XC squared plus R squared. Take the square root, get 84.4 ohms. Now we can find the maximum current. The maximum current is equal to the maximum voltage divided by impedance. The maximum voltage is equal to the square root of 2 times the RMS voltage. Plug in our numbers. We get that the maximum current through the circuit is 2.01 amps. Now that we know that, and we can also calculate phi, for which we get 0.857 radians, we can come up with our expression for the current in the circuit. 2.01 is the amplitude, the maximum current, times the sine of omega t, and we can get away with that because we are saying that at t equals 0, the current is 0. So if you plug in t equals 0 into this expression, you're taking the sine of 0, which is 0. Therefore, we satisfy this initial condition. We can plug in t is equal to 0.108 seconds, and if I did things correctly, you get a value for the current of 0.250 amps at this particular instant. We want the voltages across each of the circuit elements. Okay. VR max is equal to I max times R. And the phase shift between the voltage across the resistor and the current is 0. So I can express the voltage across the resistor as a function of time as I max times R times the sine of omega t. I know I max, I know R, I know omega, and I have a particular value for t, plug them in. We get that at 0.108 seconds, the voltage across the resistor is 13.8 volts. A similar approach to the voltage across the capacitor, I max times the capacitive reactance times the sign of, well, now we have to worry about the phase shift. The voltage across the capacitor is behind the current through the circuit by pi over 2 radians. So because it's behind, it's minus pi over 2 in the argument of the sine function. Plug in our numbers, and we get that the voltage across the capacitor at 0.108 seconds is 66.6 volts. And the voltage across the inductor. Same approach, but now the phase shift is plus pi over 2 because the voltage across the inductor leads the current through the circuit. Plug in the numbers, and we get that the voltage across the inductor is negative 194.1 volts. The resonant frequency is equal to the resonant angular frequency divided by 2 pi. The resonant angular frequency is equal to 1 over the square root of LC. Plug in our numbers, and we get that the resonant frequency is 35.2 hertz. That's all the question asked for, but do these numbers make sense? And staring at that voltage across the inductor, negative 194.1 volts, that's greater than the voltage supplied by the source. The voltage supplied by the source, 120 RMS, the maximum voltage is 169 volts, and yet somehow we're getting 194 volts out of this situation for the voltage across the inductor. Is that possible? Well, we agree with Ohm's loop rule. If we take the voltages across the resistor and the capacitor and the inductor and add them up together, we get negative 113.7 volts. We can come up with an expression for the voltage supplied by the source. It's equal to the maximum voltage of the source times the sine of omega t plus phi. And we have phi. Phi was found to be 0.857 radians. So we can plug in this. The maximum voltage is equal to the square root of 2 times the RMS voltage. Omega is 377, t is 0.108. And when we do all that, we get negative 113.5 volts, which means that it's pretty close to the 113.7 from the other three. There's some round-off error. Otherwise, if we summed up these voltages, we would get cancellation. We would satisfy Kirchhoff's loop rule. That's enough. Take care. Bye-bye.